Today we discuss about finite set. One important topics in set theory. Finite set. We already known about simple example 1, 2. This one is a set which contains two elements. One singleton 1. This one is a set contains one element. 1, 2 dot 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 n single we know about that. This one is a set contain n elements. And furthermore we discuss about that if this one 2 dot 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 thousand, then this one is a finite set contain thousands element. So how we generate finite set? How we know about finite set? We have to give a discussion or give a exact proper definition about finite set, because finite set plays important role, and obviously we know about mathematics from beginning. Then finite set is needed. We all doing work in finite set first, then we generalize in arbitrary set or infinite set. So how we handle this finite set? We handle this finite set so easily, and we also denote this set A, capital B, capital C, capital D in this way. But now we discuss the definition. First we start about the definition of set. Okay, finite set. A set is said to be finite if there is a bijective correspondence of A with some section of positive integers. A set is said to be finite when a set is finite if there is a bijective correspondence. If there is a bijective correspondence, of a with some positive integer, with some positive integers. Okay, then how we write it? We write it simply, that is a is finite if a be empty, otherwise, or if there is a bijection. If there is a bijection if a to 1 2 dot 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 n, then obviously we know about that cardinality of a equal to n. That means a be a finite set. Okay, so in this way we define finite set. A set is said to be finite. A set is said to be finite if a be empty, or if there is a bijection if a to dot 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 1 to dot 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 n. Okay, now we erase this portion, and now further discussion some important theorems about finite set, which are known finite set or understand finite set from beginning to end. Not end, for beginning to higher, that means for lower to higher, we know finite set. We start about one lemma first. Lemma says that let n be a positive integer, let n belongs to Z plus be a positive integer, and a be a set, let a be a set, and a0 belongs to a. Okay, then there exists a bijective correspondence. If of a set a with the set 1 2 dot 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 n plus 1. If and only if there exists a bijective correspondence of the set, there exists a bijective correspondence of the set A difference A0 with the set 1 2 dot 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 n. Okay, so this lemma is easily unknown. This one, how we prove it? Prove first, then we obviously going step by step process. So how we handle this? There are two implications to be proved. Let us first assume that there is a bijective correspondence. First we say that z a difference a0 to 1 to dot 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 n. Okay, be bijective. Then a function f, then a function f a2 1 2 dot 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 n plus 1 such that fx equal to gx. A difference a0 and f of a0 equal to n plus 1. Okay, then g a difference a0 to 1 to dot 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 n be bijective, then a function f such that this one, then we easily check that this one is bijective. Because g is bijective, then this means g injective and surjective. Okay, g injective and surjective means f injective and surjective, because f of a0, f of x equal to g of x and f of a0 equal to n plus 1. This one is too easy, but if we write g is injective in this way, then we erase this portion. Okay, is for the lemma also. G is injective means gx1 not equal to gx2. Okay, no, sorry, gx1 equal to gx2 implies that x1 equal to x2. Okay, this one is injective conditions, and otherwise also, or x1 not equal to x2 implies gx1 not equal to gx2. Anyone? And obviously next, g surjective means this one too easy. G surjective means there exists x belongs to a difference a0 such that fx equal to y belongs to 1 to dot 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 a. Okay, then we'll also see that if injective or not. That means if fx1 equal to if fx2, this implies that If f equal to g, then this one is gx1 equal to gx2. This implies x1 equal to x2. If f is not g, that means two options, then f x1 equal to how much? N plus a0, x1 equal to a0, and f x1 equal to n plus 1, and here x2 obviously. If others, then this one is not possible. If x1 and if x2 is not equal, then obviously here n plus 1. Then this implies that this one is a0 equal to l0. So this says that a b injective. Next we discuss further g f surjective. How f surjective? G is surjective, that means this one hold. Okay, not here g. Okay, hold. That means that there exists x belongs to a such that f of x equal to y for y belongs to 1 2 dot 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 n plus 1. Understand? So this implies that f be surjective. This satisfies that f is bijective. Not a problem at all. This satisfies that f is bijective. We all understand about that. Okay. Next we're going to further. Where is this portion? And now we also discuss further how we discuss further portion. Okay, how we discuss further portion? We prove this converse. We prove the converse. Converse is that converse very simple, but we do it. Okay, converse is that just we assume that if a2 dot 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 1 2 dot 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 n plus 1, okay, a2 1 plus n plus 1 a bijective, be bijective, then what we do, that means if a0 to be a number, if a0 equal to n plus 1, and the restriction if a difference is 0, okay, is the bijective correspondence between f difference is 0 to 1 to dot 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 n. Okay, then f restrict this one equal to this, so this one be bijective also, because one is fixed. If a0 is n plus 1, then other one is also bijective. This restrict functions. Then how we handle this one? With this one we handle otherwise, that means if this one hold, then not a problem at all, but otherwise if we take if a0 equal to m, okay, then let a1 be the point of a such that if a1 be the point of a such that f of a1 equal to n plus 1, f of a1 equal to n plus 1, then we see about that, then a1 not equal to a0, okay, a1 not equal to a0, then define a new function, which function is how much? ha2 1 to dot 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 n plus 1 equal to ha0 equal to n plus 1 and ha1 equal to m and h a equal to fx, h a equal to f a, where a belongs to a difference a0 difference a1. Okay, then we also easily check that h be bijective. Okay, then now we are back in easy case. If h difference a0 is desired bijection of this, that means h is also bijective. So we prove that this lemma, that means if f of f a2 1 to dot 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 n plus 1 if be bijective, then obviously any restriction function in if this is called g a difference a0, then g a difference a0 to n 1 to dot 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 n be bijective. Okay, then we also discuss this lemma. Now we're going to further procedure, but now today we stop here. Okay, today we stop with this lemma.